So, hello and welcome to this episode of the Opal RT Learning Journey. In today's webinar, we're going to present to you the control and operational strategies of next generation power grids based heavily on renewable energy sources. The challenges that come with the next generation grids need to be studied and understood, and suitable solutions to these challenges have to be investigated. So at the University of Duisburg-Essen, the simulation and emulation of the future's energy systems and the grid forming control strategies have been realized by combining the products of Lucas Nuller and Opal RT, and then implementing these for investigation and research purposes. My name is Daniel Brown, and today I'm joined by our panel of experts to show you how this was achieved. So, today, we have Professor Dr. Hendrik Vennegerts from the University of Duisburg-Essen. We also have Mark Versterfeld, PhD student, also at the university. We also have Francois Tempar, he's a sales engineer at Opal RT. And here with me live, Fabian Schwartz, product manager for Lucas Nuller. So today, we're going to have a look at a number of videos showing the laboratory that is at the University of Duisburg. But just before we go to that, we're going to have a look at some of the housekeeping rules. So we're going to have an interactive section towards the end of the webinar. So you can see on your screen right now, we've given you some guidance there on how you can control the platform that you're here with. So everyone is automatically muted, but you can ask questions by typing a question down into the type question here section. Please just put someone's name before there. If you've got a particular question from any of our panel of experts, please put their name in before. A couple of other things. We will be recording this webinar, so please be aware that everything will be recorded and made available at a later date. We've also noticed too that the videos that we play are going to open in a separate window. So if you're not seeing the video straight away, please just be aware that you might need to click around to see another open window somewhere on your desktop or on your computer. One last thing, a peculiarity that we found with this webinar platform is that some people have experienced problems with Bluetooth speakers or Bluetooth headphones. So if you're not hearing the tone coming through, please be aware that you might just need to switch the speakers over. So that's just out of the way. First, we're going to have a look at a video from Professor Vennegerts. So we've got everyone, obviously due to Corona, everyone's signing in from all around Germany at this stage. Unfortunately, we can't join together, but Professor Vennegerts, thank you very much for joining us. You're going to, in your video, answer some important questions such as why do we need to consider next generation grids? So would you like to perhaps give yourself a quick introduction and give us some idea about your video? Thank you.
Yeah, thank you very much, Daniel, for the introduction. Good afternoon together. My name is Hendrik Vennegerts. I'm head of the Institute of Electrical Energy Systems at the University of Duisburg-Essen. And we prepared a video in order to illustrate to the main idea and the background of our research project NextGrid, which is funded by the German Federal Ministry of Economic Affairs and Energy. And we also want to give an impression from the basic principle how we apply the equipment of both Opal RT and Lucas Nuller in our lab prepared for the research topic.
Okay, great. Thank you very much. Okay, so we're going to have a look at the video now. It's about 10 minutes. Remember, please, if you have any questions, write them down. We'll have a look at those and answer those towards the end of the webinar. And we'll see you very soon.
We have a lot of changes ongoing in the German and also in the European transmission network. One of them is an ongoing development that we need high transmission capacities because the renewable energy is concentrated regionally. This asks for new transmission lines on the one hand, so an enhanced system, but especially in Germany, we are also building a hybrid system with AC and DC lines. From this, we have some resulting challenges. We need more static, but especially more dynamic reactive power source, and we have a complex system operation due to a lot of new degrees of freedom in operation. And we need more stability controlling and maybe also other stability limits and methods to derive them. Expected solutions for this is that we have new system stabilizing controls and enhanced system operation strategies. This includes the already mentioned methods, the limits, the automation of control as well. Second keynote here is the phase out of conventional power plants in Germany, especially due to the phase out of nuclear and also coal-fired power plants. As an effect, we will have less synchronous generators in the system, operating in the system. On the other hand, renewables generation is often converter-based, if we think about especially PV and wind, and also batteries will, of course, be converter-based. Nevertheless, our actual system is based on the behavior of synchronous generators. So we would like to have a future operation which somehow substitutes the characteristics of the synchronous generators. One of them is the inertia, which is provided mechanically by the synchronous generators. The other is the instantaneous provision of reactive power current during changes in the network and also during short circuits in the network. Especially synchronous generators can provide a high reactive current due to their short time overload capability. And as a solution, actually grid forming controllers are discussed and are supposed to be the future solution for most of these challenges. Yeah, what is grid forming control? Let's start, as I said, grid forming control somehow tries to mimic the behavior of a synchronous generators. And what does a synchronous generator mean? On the right-hand side, we have this very simple model of a synchronous generator in a balanced operation. It consists of an internal voltage and any kind of internal impedance, ZG internal. And assume that we also have grid impedance connected to that synchronous generator. A synchronous generator, due to its magnetic linkages inside the generator, has, even if changes appear in the network, a constant internal voltage. That means that if there is any change in the system, let's assume that we have a sudden reduction of the grid impedance, then it will react with some retard on it. So what does that mean? Looking at a synchronous generator, this would mean if we have the sudden reduction of that grid in the first phase, the current coming from the synchronous generator will go up. And after a while, according to voltage control, it will slow down again to a new stationary value. And this is what also the, let's say, the grid forming control does. A classical control of converters, like a current-based converter control, will be very fast going to the new stationary point. It seems favorable. However, this brings, let's say, very high dynamics in the network, since the synchronous generator always tries to, by this retarding of the internal voltage, to level out the changes that have been produced by external influences. That's what, in fact, grid forming converter control tries to mimic. One of them is the so-called direct voltage control, DVC, which has been developed at our institute. Nevertheless, it's not just mimicking synchronous generator behavior. Yeah, because as a synchronous generator, the main parameters, for example, the mechanical inertia, are given by the just by the design of the synchronous generator. Now we are dealing with control, so we can almost program every kind of behavior and control and its parameterization. And therefore, there's ongoing research all over the world and also at my institute on desired grid forming behavior in the long run when we have 100% renewables. But also this behavior must cope with the transition period when we still have, let's say, classical equipment and new equipment. There might be new other stability issues and limits possible, because we have a next generation grid then with next generation behavior, and we have to investigate this. Actually, there is the need to define network codes for grid forming controls. They have not yet been defined. However, there's a time frame to do this until July 2025, because there's an obligation to think about new requirements until then. Yeah, from our lab design, first of all, we have a classical power hardware in the loop design with components of both Lucas Null and Opal RT. The Lucas Null equipment is a downsized but close to reality equipment, which especially allows us to utilize our own controls on the equipment, like for example, wind turbines. On the other hand, we have the real-time simulator, and both systems are coupled by a 4-quadrant power amplifier, which for this specific type is the first one which has been delivered to a customer by Opal RT. This classical approach already allows us to test the controls on close to reality environment, including all of natural inaccuracies and of latencies of communication. So it can prove better and closer to realistic that our controls are really working. It also allows, on the other hand, for fast prototyping of controls. So we can implement the controls in the real-time simulator as a fast prototype, then simulate it on classical equipment in the lab and show that there is no disturbing interaction in between. This is in order to govern the transition period to the future next generation system. But that's not all. We have overlaying, of course, a wide area monitoring and supervisory control system, which itself communicates with the dynamic security assessment system. This DSA system makes forecast calculations for a short time period as regards the future development of stability issues. It's built on today's knowledge about stability issues, but with this we can evaluate system stability methods of today, and we can also evaluate new methods and define new limits for system stability.
Okay, thank you very much, Professor Venegertz there. I think it's very interesting to see the challenges that we're seeing in industry there in regards to how we're going to deal with all of the energy mixes coming in. Obviously, the focus is now on renewable energies, but when you actually look at it in detail, it's not quite so easy, the implementation and all of the different mix of energy sources. So it's interesting to see the challenges that we're facing. So what we're going to do now is have a little bit more of a look into the different ways that we're tackling this, and especially at the university using the individual components. So next of all, Fabian, we're going to have a look at your video. Perhaps you would just like to introduce yourself and let everyone know
yes, sure.
a little bit about you.
Hello and welcome to the webinar from my side. I'm Fabian and I'm the product manager for power engineering at Lucas Null. I have been working in this company for 10 years and I'm in charge of the power engineering department since 2 years. During this time, I have been involved in many projects, trainings, and new developments. And one of the most interesting projects is now the cooperation with Opal RT, because the customers get training and research topic with more possibilities and benefits. And in my video now, I would like to present you the lab at the University Duisburg-Essen. Our training systems and how it's arranged with the Opal RT amplifier.
Okay. So I think the video explains itself. Again, roughly about 10 minutes worth of videos. If you have any questions about this, please just write Fabian's name down beforehand and we'll get to those a little bit later. Okay, thank you and we'll see you soon.
See you soon. Welcome to the lab at Duisburg University. I would like to give you an overview and introduction about the Lucas Null training systems. Many of our similar projects show that our training system can be used in research topics. We design them to be close as possible at the real system. To achieve this, we are using many industrial components. Last but not least, the devices in the training systems are modular and flexible to use. Institutions that perform training and research at the same time get the most benefits from the systems.
Let's start with our tour through the lab. Here on your left side we will find the Opel RT amplifier. François will give you more detailed information about this topic later. Starting with the Lucas Müller equipment, we find first a hardware prototype of our wind turbine with a synchronous generator. Although our usual hardware is designed for another type of generator, we have customized it according to the requirements of the University of Duisburg to work with a permanent excited synchronous generator. The firmware for the controller of this special equipment is being developed in cooperation with the university. Lucas Müller is very interested in bringing this product to the market very soon. Let's move to the training setup for high voltage direct current transmission lines. This system consists of two converter stations with IGBTs and a bipolar setup. It is used, for example, to learn how to couple two different power grids with different frequencies and/or voltage levels. The system allows the emulation of a short or long distance connection, replicating the most common application of transmission over long distances to reduce losses and other unwanted effects. In Europe, there are many offshore wind turbines connected to the mainland using this type of high voltage DC transmission technology. For studying this, the setup can be combined with a wind power plant training system, which I will present you later. Another important feature is the operation as a STATCOM facility for reactive power control.
Here in the corner we have our training system for synchronous generator.
Fundamental topics like manual or automatic synchronization and protection can be covered, but also more advanced application can be emulated with the same hardware. One is the behavior of different types of conventional power plants like gas turbine, hydroelectric, coal-fired or nuclear power plants. Additionally, the equipment can be used for investigating a microgrid. Here, the main generator sets the parameters to form the grid in island operation, and then the effects on frequency and voltage can be observed when connecting loads or other generations. Different control techniques like droop control are used here to stabilize the grid and reduce fluctuations.
On the other side, we have a part of our training systems for double bus bars.
It can be used to study the fundamentals of power distribution and how to switch between bus bars without interruptions of the power flow. Typically, our training systems are used standalone for the fundamentals. More advanced experiments like different grid control techniques and energy management can be done by interconnecting the training systems via double bus bars to form a micro or smart grid. For that reason, this system considers the control center of the whole power engineering laboratory. If we continue here to the right side, we have a three-phase photovoltaic system with grid-connected inverter and battery storage. This combination has become very popular in Europe houses, but also in the industry. This training system allows the student to investigate many topics on photovoltaic, starting with fundamentals like maximum power point tracking, shading effects and reactive power compensation. Later, students can learn about more complex topics like voltage regulation with a local network transformer, energy management and operating reserve. Next to the photovoltaic system, we find the training setup for wind turbines that we normally offer, including a double-fed inductive generator, which is commonly used in real applications. This system emulates the characteristic of a real Vestas V80 wind turbine, and make it possible to study topics like physical principles, synchronization of the asynchronous generator with the grid, power control and control techniques. The experiments can be performed also in the absence of wind inside the laboratory. thereby ensuring a safe environment for the students. Like I have mentioned before, a wind power plant can be combined with a high voltage DC transmission line system to study further operation modes. Since the understanding of basic concepts of power electronics is very important, we have here this training system with a self-commutated power inverter with IGBTs. Many basic experiments can be performed, such as analysis of different types of modulation and their harmonics, 1- and 4-quadrant operation and operation as a single or three-phase inverter. If we combine the inverter with an asynchronous motor, further experiments can be implemented. Now, for research purpose, we have included a MATLAB interface to reprogram the inverter and be able to test MATLAB models. And finally, after we have analyzed all the generation sources, transmission and distribution, we can now find here the energy management system. This one allows us to investigate the behavior of the systems under capacitive, inductive and resistive loads. Using this controller, we can also learn how to perform automatic reactive power compensation with capacitor battery, like is commonly used in the industry. This completes the Lukas Müller equipment of the Power Engineering Lab here at the University of Duisburg. So, now I would like to take a closer look to the PV system to show other important features. Along with all our systems, we will find interactive courses that can be installed on a computer. The multimedia platform used here is called LabSoft, and it consists of theory background, animations and wiring circuit diagrams, practical exercises, and real-time evaluation. Additionally, each course has different virtual instruments that will make the configuration of devices and data acquisition easier. Using different SCADA interfaces, our training systems can be controlled and supervised. In the example here, the common combination of photovoltaic system and battery storage is set up. The house supply is regulated by the battery storage in normal operation. In manual control mode, the battery storage can be charged or discharged by adjusting the power set point with a slider. First, the charging is set to 750 watts. The energy flow can now be observed in the SCADA interface. Let's change it here to discharge. And check now this energy flow change. On the inverter side, we observe the slider controller for the D-rating. According to the country-specified regulations for renewable energy sources, power reduction should be available for reducing active power in order to avoid network overload. This was just an overview of the lab and training systems. We will continue here with the Opel RT amplifier presented by François. I'd be very interested to hear your comments at the end of the webinar. Thanks for your attention.
Okay, welcome back. Fabian, thank you very much for that overview into the laboratory. It's very interesting to see how that one is set up. So this one is mainly used for research, but there is also training that can be done with that as well. Is there really a mix of the two systems, or?
Yes, that's the idea behind this. So our systems are designed as training systems, and in this configuration, they can be used for research topics too, because we designed them to be close as possible to real systems.
Okay, that's something that Professor Venegertz mentioned during his presentation is the Lukas Müller systems, they're downsized, so, but very close to reality, which I think is
yes.
a very good way to do the training, but also to do the research there. And again, looking at this energy mix, how it's changing is really interesting. It's not quite so simple to integrate all these forms of energy into the system. So we also seen the system there. Is that very static, or is that something where it's modular that you can change out as well according to what you need to learn? So,
yeah, we have setups for the application, so the typical PV, but you understand how this application is working, and later you can fully customize your setup to your needs. So you're very modular and flexible in the use of our systems.
okay, so we've seen there photovoltaic, wind power, things like that, but you can have conventional. You also showed us how you have like synchronous generator. So
yeah.
anything is
possible. Yes.
Yeah.
So we have some customers where are in the power distribution, and they replicate their real system or part of a real system with our training system to study some behaviors inside their normal real system, downsized for their trainees.
Okay. And I guess that's where we're coming to the next important step in this cooperation here is the amplifier, of course, the heart of the system here. So we'll have a look now and we'll introduce the next expert for today, Francois. Thank you for joining us.
Thank you, Daniel, for the introduction.
Yeah, perhaps you could give us a very quick overview of what we might expect to see in this video of yours and how that might be used.
Yes,
thank you.
Provide this overview. So my name is François Tempé. I'm working as a technical and sales engineer at Opal RT in Germany, and I've been working for 7 years now for Opal, doing a lot of first commissioning and training all around the world, and especially in Europe. And I had the chance to make the commissioning of the first power hardware in the loop test bench delivered by Opal RT in the entire world. It was for University of Duisburg-Essen, so I'm quite excited to present this test bench today in the UD laboratory. And
so
during this video,
sorry, Francois, this is the very first system. Is that what you said?
Exactly, the first delivered in the world. Yes, exactly.
Wow.
Yes, so that's why it's very good to have both UD and you, Lucas Noulet, for this webinar. And during this video, I'm going to present you the different components of this OP1420 microgrid PHIL test bench in the UD laboratory. So it will be easier for you to understand how the link can be done between the simulation and the physical devices from Lucas Noulet, presented by Fabian previously. And then we will have the chance to see some demonstrations from Mark using all these components.
Okay, fantastic. Well, we'll have a look at the video now. Again, if you've got any questions, please let us know in the question area, and we'll have a look at those after. So thank you, Francois, and we'll be back soon.
Today, I'm going to show you our 4-quadrant amplifier and the microgrid test bench in which the amplifier is located. To begin with, let me reminding you the PHIL concept. Power hardware in the loop is an extension of hardware in the loop in which the real-time simulation environment is capable of exchanging power with external devices under test. These DUTs are connected to the simulation using a power amplifier, and this power amplifier is controlled by the simulation. Universities around the world are rapidly adopting PHIL technologies, which is a significant benefit for their researchers and students. However, the time, the cost, and the complexity to build such test benches is very high. It remains a challenge. This is the reason why Opal RT developed the OP1420 Power Hardware in the Loop microgrid test bench. It is a turnkey platform which is modular, flexible, and highly reconfigurable. It is an ideal simulation platform which allows users to to do hands-on experiments by testing external components under various operating conditions. We can mention a few applications, such as testing microgrid controllers and protection systems, AC and DC microgrid simulation with external DER and nonlinear loads, and integration of microgrid within large power system. Components such as Lucas Noulet test benches presented by Fabian previously can easily be connected to this test bench. We could think about having PV panel connected to group 1 of this test bench, a storage system able to source and sync power connected to group 2, and a DC network emulation connected to group 3, which makes this test bench highly scalable and configurable. I think now it's time to have a deeper look at each component of this test bench by looking at the OP1420 PHIL microgrid test bench in University Duisburg-Essen laboratory. This safety box provides low voltage supply to other components and controls the three-phase input power on the front side. It also allows to disconnect DC sources and high power components of the test bench in case of fault. The OP5707 real-time simulator allows to run power system models in real time over several CPU cores. This OP5707 real-time simulator is composed by Intel Xeon CPU cores, which allows to run the simulation in real time. And you can exchange information with external controllers using analog and digital input-output boards. These I/O boards are directly managed by a Xilinx Virtex 7 FPGA board. As you can see here, you also have an optical connectivity, which is a high-speed, low-latency communication link with the power amplifier. It is required to ensure stability of the PHIL system. The models running in this real-time simulator are designed using MATLAB Simulink, and RTLab software Artemis Solver from Opal RT ensures the real-time constraints to be respected by having a computation time lower than the time step and decoupling the power system model on several CPU cores. Opal RT developed some special blocks which are integrated in RTLab library within MATLAB Simulink toolbox, which allows to send voltage and current set point from the simulation to the power amplifier and receive measurements from the amplifier to the simulator. This set point can be sent from the CPU, but you will be limited by the CPU time step. So if you have running power system model at 50 microseconds, only one point every 50 microseconds can be sent from the simulator to the amplifier. For high frequencies, higher than 1 or 2 kilohertz, we highly advise using the FPGA generation to send set points. You will benefit from a higher resolution thanks to the FPGA clock. Microgrid models are provided by Opal RT. They are composed by wind turbine, battery energy storage system, PV plant, diesel generator, aggregated loads, even microgrid controllers. You could replace the PV panel simulated by the Lucas Noulet PV test bench as presented previously by Fabian in the model. And the results of these PHIL experiments can be directly displayed within a LabVIEW panel composed by scopes, graphs, widgets, sliders, and the operator can directly communicate with this simulation on the fly. We can switch now to this microgrid bus bar panel. It is composed by padlockable connector disconnectors, which allows to manually connect external DER to the internal bus bar. This actuator push button allows the contactor to close to have the physical connection of this DER to the bus bar. Each DER is composed by 4 banana plug connectors for the 3 phases and the neutral. And there is a selector here, selector button. If it's set to local, then the connection of external DER to the internal bus bar can be done with this push button actuator. If it's remote, then the user can remotely control the external DER connection directly from the model by using a digital signal sent from the model to the microgrid bus bar. Interesting component, the power meter panel allows measurements to be displayed on the fly, such as voltage, current, active power, reactive power, apparent power, power factor, total harmonic distortion. And we can benefit from these measurements thanks to current transformer and potential transformers connected to the 4 microgrid bus bar DER connections. Let's switch to the heart of this test bench with the OP8110 4-quadrant power hardware-in-the-loop amplifier. This one is composed by 2 groups of 3-phase amplifiers, while this one is composed by 1 group of 3-phase. So each group has 5 kilowatts, and it can be operated in AC mode, DC mode, voltage mode, and current mode as well. In terms of performance, the innovative technology based on soft switching cells with silicon carbide transistors is used, which allows to have no dissipation and an energy efficiency higher than 96%. In terms of fidelity, the bandwidth is up to 10 kilohertz at -3 decibel, and total harmonic distortion lower than 0.5%. In terms of safety, we have, for example, over voltage, over current, under voltage, short circuits, and over temperature protections. In terms of connectivity, optical fiber links are connected between these power amplifiers and the real-time simulator. It uses small form factor pluggable connectors, and to ensure a very fast communication, Aurora communication protocol is implemented within the simulator FPGA and within the power amplifier FPGA. So we have a communication higher than 5 gigabits per second, which is key to ensure the stability of the power hardware-in-the-loop setup. Finally, we have here 3 DC sources of 6 kilowatt, 500 volt DC. Each of them are controlling 1 group of 3-phase power amplifier to sink and source power. It concludes the presentation of the OP1420 PHIL microgrid test bench. And with that, I would like to give the floor to Mark, who is going to present a live PHIL experiment.
Okay, so welcome back, and thank you very much, Francois, for showing the video, explaining the system quite well. Gives us a good understanding of how the system operates and how it can be used into the various systems. Francois, if I could just ask you there a question. Something that I understand about the system is it's the only system on the market that is able to put the energy back into the grid, as opposed to normally we have a chopper break or a resistor bank to waste the energy. This is the only system that will actually put the energy back into the grid to save it. Is that correct?
Yes, it's correct, Daniel. So there are 2 main technologies for power amplifier. One is based on what we call linear power amplifiers, so you can have a very large bandwidth but usually you will be able to sink only 1/3 of what you can source. So to get rid of this limitation, you can add some resistor banks to dissipate the energy. So it's a very good solution for some application which require very high bandwidths. If the bandwidth is not a key aspect of the application, then switching technologies is very popular. But usually you won't be able to reach very high frequency, and there would be some energy dissipation which would require some cooling systems. At Opal RT, for our first power amplifier, we've decided to use quite an innovative technology based on soft switching cells and silicon carbide transistors, which allows to get rid of this energy dissipation and avoid any cooling systems to be implemented.
Okay, fantastic. Yeah, thank you very much. Okay, we're coming now to our last expert today, and the person who's putting everything together and really putting it into action. So Mark Versterfeld, thank you very much for joining us. It's great to see. We're going to have a look at your video about how this is being implemented and what we are all learning by putting this together. So yeah, thank you, and we're looking forward to your video. Would you like to perhaps just give us a quick word about yourself and what we might expect from your video?
Yeah, hi, good afternoon and good morning, everyone. I'm very pleased to be here today and that you joined. And thank you, Daniel, for the opening words. First, to me, I'm a research assistant at the University Duisburg-Essen in the Institute of Hendrik Vennegaerts, the electrical energy systems. Some words first. With the equipment of Lukas Müller, which was presented by Fabian, and the brand new amplifier from Opal RT shown by Francois, we are now able to take our project NextGrid to a whole new level. Actually, we are able to implement our ideas about grid forming converter into the real world. So with everything has been said so far about the individual components, we will show you in the upcoming video a small demonstration we've prepared for you, a short network split scenario.
Okay, fantastic. And we can see you're actually in the laboratory right there now, so you're really living this this laboratory. It's great to see.
Yeah, I mean, it's a nice laboratory, so why not?
Great. Okay, so we'll have a look at your video. We're still waiting for some questions to come through, so we've got a panel of experts here, so please make use of them while they're available for today. So again, we'll be back in a few minutes, and look forward to speaking to you again soon.
Yeah, like we said earlier, I will show you the behavior of our grid forming control in a grid split scenario. With this convenient and easy to use power hardware in the loop concept provided by Opal RT in cooperation with Lukas Müller, we could easily prove the potential of the developed concepts and validate their applicability, taking into account typical communication interfaces with their possible latencies as well as inevitable parameter and measurement inaccuracies. First, let us talk about the theoretical background. Among other, a simplified method for the description of the synchronous generator behavior is a swing equation. It shows the correlation between acceleration or deceleration of the rotor and the power delivered by the prime mover or consumed by the electrical grid. For a power equilibrium, the rotor will not change its actual frequency. The rotor will be slowed down when the electrical loads will be increased with a static power infeed from the prime mover. But this just tells us whether the frequency will change or not. Without any additional value, it will not give us a specific frequency. This will be done by the droop curve. The droop curve is part of the primary control. Without secondary and tertiary control, it will give us a resulting frequency. Let us look at the power plant with 800 megawatts of nominal power. In normal operation, its prime mover will provide the needed power with a nominal frequency at 50 Hertz. When the frequency drops, it provides more power. Vice versa, when there is more power needed, it leads to a lower frequency. To summarize, Power deviations will lead to grid frequency deviations, and grid frequency deviations will lead to an adjustment of the power in feed from the prime mover. In the end, there will be a stationary grid frequency, but it will not be the nominal frequency without any additional control forms. So, why do we need this? In the demonstration that follows, we will look at the grid splitting scenario. In nearly most of the cases, the active power balance of the remaining grid sections are not balanced due to the active power flow of the coupling lines that are switched off. So, we will see frequency deviations. We will look at this process and diagrams in a moment. The test grid consists of a simulated part with loads, transmission lines, and a wind turbine. The real power hardware in the loop test bench consists of a real synchronous machine and a resistive load. The wind turbine, which is simulated, is controlled by a grid-forming control structure named DVC. The real synchronous generator is set up as a constant power feeder with low inertia. At the beginning, we have a power flow of about 50 megawatts from our wind turbine to the other part of the simulated grid, in addition to our about 450 watt ohmic load of our test bench. Of course, the ohmic load will be scaled up, so the simulated grid will see about 150 megawatts of load. Then we will increase the power in feed from the real generator, which will decrease the simulative load. After we split the system with the breaker in position B, we will force our wind turbine to synchronize our test bench with the simulated generator, and we can connect both grids again. So, let's activate the simulation and start the amplifier. We have to set up our DC sources. We will set up them with 500 volts and let's say 5 ampere in bidirectional ways. Okay, now we have to activate them. And now we activate the outputs. In the meanwhile, our simulations are already running, so we can see here some actual values from the simulated wind turbine, from the simulated synchronous machine, and from our absolute amplifier. The power and reactive power, and some values for the frequency and voltage. So now let's activate the output. So as you can see now, here the actual voltage is displayed and the measured current. So you can see we have a current, and in our resistive load here, you see an actual power of, let's say, 450 watts. And as I said, the real power will be scaled up so that the simulative grid see around 150 megawatts. As you can see, the frequency is about 49.7 Hertz, since the primary control of the simulated generator is active. Now, let us increase the power in feed from the real synchronous generator. Since the generated load is increased, the simulated load will be decreased. So the frequency will rise due to the mentioned PF droop curve. Now, let us split the grid in two independent systems. As you remember from the grid topology, we had a power flow from our simulated wind turbine to the rest of the simulated grid. Since this is not possible anymore, The simulated synchronous generator has to provide all the loads in this remaining grid network by its own. As the load increases, the frequency will decrease until it found a stable operation point within the Drude curve. On the other hand, the wind turbine doesn't have to provide the power anymore for the simulated grid, so the frequency will rise. In this case here, the wind turbine has a grid forming control, visible in the spikes right at the split moment. There are angular steps, thus frequency deviations, which will result in adjustment of the sudden change grid impedance. With grid following control, the frequency either would not be catched, so the system becomes unstable, or the absolute frequency deviation would rise much higher. To connect both grids again, we have to synchronize them. Since we can control our wind turbine in a more general way than the synchronous machine, we will force it to achieve the same frequency and an acceptable angle between these two grids. Okay, let's force the wind turbine to synchronize with the simulated synchronous machine. We are now able to connect the grids. Since we were forcing the wind turbine to reach the simulated synchronous machine's grid frequency, then its designated operation point on its Drude curve, it will result in a clearing process. Here, both primary controls will achieve an equilibrium so that the pre-split frequency is achieved again. You saw, with this field setup, it is easy for us to demonstrate important systems reaction or modeling complex systems which will be driven by our real power hardware.
Okay, so welcome back. So that was our last video. Mark, thank you very much for that. I think for me, one of the important things that you said there, that this laboratory with all of the equipment that you have there really gives you a chance to prove the developed concepts and their applications. It gives you a chance to come up with new ideas, but then to put them in practice and see if they actually work in practice. That's what I find so interesting about this cooperation. So just Mark on that, what would you say is so special and unique about this laboratory? Is there anything that you found by being so deeply involved with it?
Yeah, actually there are 2 points in particular are worth mentioning here. First of all, with the Lucas Müller equipment, we are not only able to set up special test cases, but due to the variety of devices and possible applications of the individual components, we are able to present a large number of test cases at the same time. Further, with the new amplifier of Opal RT, we are of course able to enable power hardware in the loop advantages like fully customizable grid and fault scenarios. So even more diversity because our grid is very strong here and without much deviation. In addition, it has a convenient operation concept and is fully integrated in our real-time simulator. Of course, we could also use some additional extensive and of course expensive hardware to generate our wished grid behavior. But with this power hardware in the loop application here, it will be much easier and provide us with a broader variety of possibilities.
Okay, fantastic. You also said that you use the amplifier for customizable grid solutions, but not here. Could you maybe just explain that for me, please?
Yeah, that is correct. Let's say the traditional way would be to provide a customizable grid for real power hardware. Because of the freely programmable real-time simulator, in combination with the amplifier, we can even use it for rapid prototyping before we set our hardware, like rapid pre-prototyping.
Okay, very interesting. Okay, so we've started to get some questions come through now, and we've actually got one for you, Mark, here. So what kind of controllers have you used to control active power, frequency, voltage, and reactive power? Is there anything you can say about that, Mark?
First of all, which controller. I mean, for our grid firming controller here, the reactive power is just provided by the voltage stability and the voltage level. Since this is we want to apply a realistic grid, so relatively inductive behavior. The power will be just. This is a key point of the grid forming behavior. The power will just be provided from the grid forming wind turbine in the needs of the frequency stability. So for frequency, we have, in this particular case, we have implemented a swing equation, among others, but in general, a swing equation for the wind turbine to mimic the behavior of the synchronous machine.
Okay, fantastic.
Also, the training system from us we saw in Mark's presentation was our microgrid application, and there we have different controllers integrated, and also it's customizable. So if you like to change something, there's a PLC in the background that can be modified, and troop control, and these things are implemented by us. Just additional information about the other side.
Perfect.
Yeah.
So we're getting a lot of the questions coming in now. We've got a few people asking about will the webinar, or how will they get a recording of the webinar? You'll get some emails from Opel RT, and there'll also be a chance to get that from Lukas Nuller as well. So you'll get some additional information towards the end in email format or on Lukas Nuller website. So it might take a couple of days to make that available, but you'll get the information sent out to you as soon as that's done. Okay, Francois, we have a question here for you. Can the power amplifier work with OP5142? Is there anything, sounds like a customer which already has some of your equipment, sounds like they're looking to upgrade or extend their program.
Yes. So to communicate with the power amplifier, we are using these optical fiber links. So we need to have SFP connectors in front of the real-time simulator chassis. And unfortunately, with the so OP5142, which is a Spartan 3 FPGA board, I think it's this one, but I'm sure it doesn't have any the ability to have SFP ports. So to have this SFP port and the Aurora communication protocol implemented in the FPGA, we have to use our Kintex 7 FPGA boards with the OP4510 or Virtex 7 FPGA board with the OP5707, the one we've seen today at UD.
Okay, thank you. So Mark, we have another question for you. Thank you, Mark, for this presentation. I have two questions. How do you deal with overcurrent and initial synchro with grid forming? What kind of GF control are you using? Thanks.
Yeah, thank you for the question. Great question. First, with the overcurrent, there are typical ways for dealing with it. The most common way is to switch from any kind of grid sensing to PLL sensed mode, but this will create some not nice behavior, and it is not predictable in any power flow calculation or something like that. So for now, we did not implement one specific overcurrent here. We have two overcurrents, like first handling the voltage levels, but this will of course affect the grid. So we will implement the mode that we will use several transformations for the modes for positive and negative sequence to get the angle which is needed, or the power which is needed, and the current flow which is needed to provide the actual needed power and voltages. So yeah, it's not used, it's not implemented yet in this case you saw, but yes, we will use both ways. And initial synco, I guess you mean synchronizing with the grid forming. In this way, it just has synchronized like the first milliseconds in the real-time simulator, but later on, its controller will just sensing the whole time the voltages, so it will either provide the reference power, like in a wind farm or something like that, or in static voltage regulations. Yes. So the synchronization is done in every second. And the control which you're using here is the direct voltage control, which is which was developed by our institute here.
Okay, thank you very much, Mark. Okay, Mark, you're very popular in the questions here today. So I've got a few more coming to you. So we have another one here. What is the software you are using when it comes to visualizations on OPL on testing grid? I'm addressing to Mr. Meyer.
Yes. In this case here, we just have implemented, like you saw, the grid in MATLAB Simulink. So we are using some specialized power system toolboxes, and they can run power flow simulations. So these are just used here, which is the main benefit from Opal RT, which we can use the Simulink model for the programming there. Yes.
Okay. Okay, while I have you, Mark, there's a couple more questions. So you talked about scaling the power from watts to megawatts. Could you please discuss that controllers process which powers in watts or megawatts?
Yeah, I mean, we have a test bench here for, let's say, maximum load is 15 kilowatts. So a real wind turbine with 12 megawatts or something like that, or a park with hundreds of megawatts will not sense this little amount of power here. So we have scaled them up. And this is this key fact of power hardware in the loop, that you can mimic a special behavior here in our lab and just scale them up, the power flow, like you saw. We have scaled it up with 333, let's say this one. And yeah, so it will become more relevant in the distribution or transmission grid, which we want to do research on.
Okay. One last question for you here, Mark. How Opal RT simulator can be used for phasor measurement unit standard compliance testing? So IEEE C37.118. Do you know anything about that, Mark? Is that something you can speak to?
Yes. I mean, it's not coincidence, because we just using this this method tool, let's say method. Maybe you saw it in my video, but in the back of me there is PMU, like a distance protection unit from Siemens, which we will implement in our grid 2, and we will extend our research for DSA and also dynamical security assessment systems and wide area measuring, which uses a C32.118. So we have a real system here, real data concatenator and so on. But Opal RT itself can provide it by its own. We will simulate in the net, in the grid, our own PMUs, our phasor measurement units with this specific protocol, and we will just send them to the real DSA system. So it can provide the simulated phasor measurements units and can act as a master, so that you can create a DSA on the real-time simulator itself.
Okay, great. Fantastic. Thanks, Mark. Thank you for your expertise here as well. It's really enlightening for everyone, obviously sending through lots of questions, so it's great to get those answers from you. Okay, Professor Vennegaerts, there's a couple of questions for you here as well now. So does the grid forming control require deloading of wind farms for fast frequency support during low frequency events? Is that something you can give us some ideas about, please?
As if you think about grid forming control to provide any kind of inertia or fast grid forming control, of course, this requires deloading of wind farms. If this is possible to take this energy or store this energy the other way around, also in the rotor system, this is still ongoing research. There have been a lot of research on this, but there's still research to which dynamic this is possible. Of course, there are a lot of solutions discussed in the research world. For example, adding a small battery storage to the DC link in the converter, not only for wind farms, also for grid forming control of STATCOMs or other ways. So this is something that has still to be investigated. But to be clear about that question, at low frequency events, of course, the grid forming control requires some deloading to take the energy somewhere. Yeah, it always requires some energy behind.
Okay. And another question to you as well. How do you define virtual inertia in grid forming inverter?
Yeah, it's clear that it's asked for a clear definition. Yeah, if we want to really mimic the synchronous generator, virtual inertia really means that it's instantaneous provision of additional or minor electrical power if the frequency is decreasing or increasing. So instantaneous, not built on by any kind of control, even if it takes only a few microseconds, like in any kind of fast frequency response of converters. How this is derived can have different ways. Yeah, when we think about direct voltage control, in the principle how it is actually been published by this institute, we see that this is already indirectly supplied by the PLL, because this has some delay and is therefore retarding the voltage change. Yeah, however, of course, it is possible to parameterize this, and there might be any other synchronization methods, for example, using a virtual synchronous machine behind, or the equations of a synchronous machine, which really would provide instantaneous virtual inertia.
Okay, thank you for the comprehensive answer there. Okay, so Mark, unfortunately, you're getting more and more questions coming in. Oh, fortunately, it's showing your expertise here. So we'll just perhaps have a look at those as well. So there's a question here. In my institution, we bought some equipment from Lucas Nuller. So Lucas Nuller used Droop controller to control microgrid, master and slave, and you talked about Droop curve. So I would like to know, how did you combine Droop curve and Droop controllers, please, Mark?
Yeah, thanks. In our control, we did not implement the Droop controller or something like that. I just mentioned this to make sure that we want to mimic the frequency behavior from a synchronous machine. So when there's more power needed, the frequency just have to decrease. So as you saw in the diagrams, the frequency for a synchronous machine, which has increased load, has decreased, and for our wind turbine, which has been deloaded from the rest of the grid, it has an increased frequency. So it was just to mimic the behavior.
Okay. Okay, so we're actually running over time, so I'll just go through the last couple of questions quickly. Another one for you, Mark. Is the amplifier confronted with stability issues, and in case, how do you handle it? E.g., low pass filter in current feedback. Have you had any experience with that whatsoever?
Yeah, very nice question. Of course, at some point, because it is just a closed loop control, like the real-time simulator and our complete grid here, it will face stability issues. But this is handled by, in our case, we will implement some, or we have implemented some interface algorithms named ideal transformer method, which is commonly most used here. And with low pass filter, just a low pass filter, it will be very hard for you, because at some kinds the grid will require, or let's say you simulate a synchronous machine, there will be short circuit and you have a DC current. So this will be just out filtered. So a low pass filter in particular will not work. Of course, you can use high pass filter on low pass filter. So in our application here, we will use the ideal transformer method, but of course we will look for other interface algorithms too.
Okay, perfect, thank you. Okay, Fabian, we have a question here related about hardware. So we've seen the type of hardware implemented there. Someone's asking, is the choice of 400 volts, 450 watts voltage and power level, is that mandatory, or can they also use a lower voltage to make it more safe as well?
I guess this is a question for Francois too. So our hardware we have in two versions, one for the US market with 208 volts and 400 for the European grid. And yes, you can modify the MOS application to run lower voltage, but we also have industrial devices like the PV inverter that needs the 400 volts. So there's no way to reduce the voltage, because yeah, it's in the firmware of a device, industrial device I told before. In the US market, we are using at this point a transformer for 208, 400 volts. And maybe Francois can say something to the amplifier. Yes.
Yes, I can mention something on the power amplifier side. So this power amplifier can work also on 120 volts, especially for the North American market, and then of course at 230 volts. And then the user can define his own set point within the model. So you could choose to have sine wave at 50, 100, 150 volts. It's really up to you. So the maximum voltage in AC mode would be 120% of the nominal voltage. But then within this range, you can choose more or less whatever you want. You could also do DC. So this power amplifier could be used for DC applications, especially if you want to connect some batteries. And then we can go up to 400 volt DC. So it can work in AC and DC mode as well.
Okay, fantastic. Okay, so Francois, while we have you, also one last question there for you. Sounds like a very product-specific question. So, can we do an upgrade from Spartan 3 to Artex 7 so we can have the benefits from SFP ports? Are you able to answer anything about that?
Yes, it's a good complementary question based on my previous answer. So yes, in my previous answer, I mentioned that we cannot use SFP port with this Spartan 3 FPGA board. It's just worth mentioning that, of course, there is an option on which you can upgrade the system by adding an FPGA board which can support these SFP ports. So it's definitely something we can provide to be able to have SFP ports and Aurora communication protocol. Yeah. So the answer is yes, we can do this upgrade.
Fantastic. Okay, so we're actually 15 minutes over our time. That's how many questions came through in the end. So it's really great to see everyone. We've literally had people looking at the attendee list from all around the world joining in, from the east right through to the west. So it's great to have everyone joining in and being so engaged, asking the questions. So from our side, I'll hand it over to Francois to say goodbye, because this is a Opal RT webinar. But before we go, I'd just like to say thank you very much for joining us here. It's great to be involved. And thank you to our experts for giving so much great information over as well. So Francois, would you like to send us off on the end of this webinar, please?
Yes, thank you. First of all, I would like to thank you, Lucas Noulet, so Daniel, Fabian. It was, an outstanding support from your side for the organization of this webinar. So again, thank you very much for your professionalism. Then I would like to thank the University Duisburg-Essen, so Professor Venegert, Mark. Your input has been very highly appreciated, and it was very interesting to see what you managed to do in only a couple of months, because I remember I was there only 3 months ago. So the work you've done these 3 last months is very is impressive, and I'm very glad to collaborate with you. To conclude, I would also like to thank all the attendees. Finally, the webinar lasted 15 minutes longer than expected, and I think it's a good news because you had a lot of questions. So I'm very happy that we managed to create this interaction with you, even if we are in a situation when we cannot have a physical conferences. It's nice to see that you are still here to attend webinars and to ask questions about our customer applications. Thank you all for attending this webinar. We hope you've enjoyed it, and please don't forget to answer the survey you will see when you close the webinar, and stay posted for our next Opal RT Learning Journey webinars. Have a nice day. Bye.
Bye.
Thank you, everyone.
Bye.